Hello, my name is Marie, and today I'm here to talk to you about my research project. But first, I'd like to start off with a question. What if your dental care could work for you? Literally. While you go about your day, imagine a 3D printed tooth cap infused with fluoride salts designed to release just the right amount of fluoride to prevent cavities without overexposing your body. My project brings together cutting edge SLA 3D printing and biomaterials to create a personalized, efficient, and safer alternative to traditional fluoride treatments. This innovation has the potential to transform preventative dental care worldwide. Science, technology, and a healthier smile. So, without further ado, let's make it happen. Every day, millions of people brush their teeth, hoping to keep cavities at bay. But here's the catch: fluoride in toothpaste and varnishes in dental clinics to help treat cavities is temporary, inconsistent, and can often lead to overexposure, causing fluorosis, which is the increase in fluoride in gum in the oral cavity. The problem: cavities form when acid breaks down enamel, leading to demineralization. While fluoride can help remineralize and strengthen enamel, current methods don't provide long term protection. What if we could change that? My project introduces a controlled release fluoride device, essentially a 3D printed tooth cap infused with fluoride salts. This innovation provides continuous protection right at the source, reducing the risk of systematic overexposure while keeping your teeth healthy. With this technology, I'm taking a step towards smarter, more effective dental care because strong smiles start with a strong science. In the image on over here, you can see how demineralization actively in enters the enamel and the significance and the detrimental effects that it has. So the chemistry behind it. Cavities aren't just painful, they're expensive to fix. While toothpaste seems like an easy solution, it's almost like a band-aid on a wound. It's not always effective. And costly procedures like laser therapy can leave teeth even more damaged and potentially lead to fluorosis or other major issues. The real challenge: finding a solution that's affordable, accessible, and long lasting. That's where fluoride comes in. Fluoride is naturally found in saliva and has been used in toothpaste to reduce fluid movement in dental tubules. But what if we could take it a step further? The image here shows how fluoride works with magic by disrupting bacterial metabolism and promoting remineralization. It reacts with hydroxyapatite to form fluorapatite, which is far more resistant to acid dissolution. This makes teeth stronger and more protected against decay. Now, take a moment and imagine a 3D printed fluoride device attached to the tooth, continuously releasing fluoride right when it's needed. While past attempts used PCL-based devices, they weren't user-friendly or effective in releasing fluoride. But new research like biomimetic enamel technologies introduces dentine phosphoprotein-derived peptides, which mimic natural enamel-building proteins, capturing calcium and phosphate ions to strengthen the teeth from within. By combining these advanced techniques, we can 3D print a device that not only prevents cavities, but also enhances bone integration and enamel regeneration. This means better dental health, lower costs, and a future where stronger smiles are accessible to each American. What if we could stop cavities before they even start? That's exactly what my project aims to do. Imagine a 3D printed fluoride release cap that protects your teeth without the need for a constant brushing or expensive treatments. The process begins by designing the cap in SolidWorks, where we create a perfect 3D model for printing. Next, we infuse the resin with fluoride salts, ensuring a steady fluoride release. We have a 1:10 ratio between resin and fluoride salt, and this allows for teeth to not be overly exposed to fluoride and cause fluorosis. Then it's time for SLA printing. We use the Formlabs Form 2 when bringing our fluoride-infused cap to life with precision and detail. But how do we know it actually works? Well, we mimic the human mouth by creating a pH-buffered solution that imitates saliva. This is between 5 to 6.5 pH. Then, at specific timed intervals, which is 30 minutes, 1 hour, 1 day, and 5 days, we collect samples to measure how much fluoride is released. Finally, we analyze these samples using a UV-Vis spec, giving us precise data on fluoride concentration. My research focuses on designing a 3D printed fluoride releasing oral device that delivers fluoride in a more targeted and sustainable way. Here's the chemistry behind it. I start by incorporating fluoride salts into a liquid resin before printing and using a stereolithography, also known as an SLA, throughout this presentation. SLA works by curing the resin layer by layer with a UV laser, trapping fluoride ions inside the solid polymer matrix. I specifically use the rigid 10K resin by Formlabs because the fluoride ions are able to release once and penetrate through once inside of the pH buffered solution. The pH buffered solution mimics the oral cavity, and this is crucial because the slightly acidic environment of the mouth gradually breaks down the polymer structure, allowing fluoride ions to diffuse out over time. The rate of release depends on polymer porosity, fluoride solubility, and interactions with the surrounding solution. To track fluoride release, I take samples at specific timed intervals, 30 minutes, 1 hour, 1 day, and 5 days, as previously mentioned, and analyze them using a UV-vis spec. This technique detects fluoride concentration by measuring how the solution absorbs light, giving me precise data on how much fluoride is exactly being released at each stage. By optimizing this process, my research aims to create a controlled, long-lasting fluoride delivery system, a potential game changer for cavity prevention and oral health. Now let's get into my preliminary data. This table presents preliminary data on the release of fluoride over time, measured through absorbance values. The absorbance values decrease over time, indicating that fluoride is being released as potassium fluoride disassociates. At 30 minutes, the absorbance is 0.0014, which then drops to 0.0012 at 1 hour. A significant drop is observed by 1 day, reaching 0.000783, followed by a smaller decrease in 0.000656 at 5 days. This trend suggests that most of the fluoride release occurs early, with a steep decline initially and a more gradual decrease afterward. This could be due to the rapid dissociation of potassium fluoride in solution, followed by a slower equilibrium process where fluoride ions interact with other components in the environment. The handwritten note at the bottom indicates a big change in absorbance between 30 minutes and 1 day, and a smaller change between 1 day and 5 days, supporting this interpretation. These findings are important for understanding fluoride release dynamics, and could be useful for applications such as controlled fluoride delivery or environmental fluoride monitoring. And finally, here are my resources. Thank you so much for taking the time out of your day to listen to my presentation, and I hope you enjoyed.